Hello scholars, welcome. Mr. Hinkle here. We're talking about the Earth as a system, a set of interacting parts forming a whole, and interactions that occur within Earth's spheres, the hydrosphere, biosphere, atmosphere, lithosphere, cryosphere, and exosphere, and how we measure them. The purpose of this lecture is to describe the various scales of measurement through time and space in Earth systems science. So, scales of measurement. The Earth system has forcing events that move a system in a particular direction, creating feedbacks. And we can look at the variability through, and whenever you're thinking about variability, whenever I'm thinking about a system and how it functions and how it operates, I'm thinking about, first, how does it work? And then second, how does it change? And part of that change, it happens not only through time, but also the spatial distribution, the geographic variability, as well as the temporal. So we're really thinking about time and space for variability. So that's what we're getting into in this lecture. Let's look at space. So we have global. This is a forcing event that, global geography, excuse me. This is a forcing event that affects the entire planet. Okay, so why don't we do this? Time and space, I got that. What I really want to say is we're going to do geography here. If we're going to make a short list, which is space. We're starting with global effects. Large volcanic eruption, the 1815 Mount Tambora eruption created the year without a summer, led to global cooling. That is a global geographic event. Likely, in Earth's history, the entire planet has frozen over, as evidenced by dropstones and various alternating layers of limestone and classic sedimentary rocks in Earth's marine deposits, affecting the entire planet. So effects that are on a global scale are global geography. Regional is going to be when you have forcing events or feedback responses that affect different locations differently. Biodiversity is a great example of this. There's way more different types of species in the equator where you have more sunlight, warmer temperatures than there is at the poles. So we see regional differences in the amount of biodiversity, the species richness at various latitudes. And latitude in general usually creates variability because of the amount of heat and sunlight that occurs from the equator to the poles. So regional is important. We've also got continental interiors versus coasts versus oceans. Oceans have water has a high heat capacity, and therefore oceans can absorb a lot more heat without changing their temperature. Land, shunk, turn the light on, turn the sun on, and boom, temperatures skyrocket. So we see interiors experiencing larger temperature fluctuations than coastal environments. Another example of regional. So we'll go biodiversity, temps. What do we have here? Snowball Earth, which is global cooling, for example. I.e., for example, let's keep it going. Local is forcing events that vary widely, and you see effects in one place and not another. Here, look at this. You have trees that are inside of the drainage where the ridges are dry. Mountains and forests can create local effects. When you have ocean water and then mountains like so, you can get a lot of rain, clouds and rain on the windward side, and then it's dry on the leeward side. One mountain range, local differences from one side to the other. So for local, we'll do hill slopes and mountains. Space. Now let's look at time. So time scales, yeah, you're probably guessing it. It's going to be short, medium, and long, right? So we've got daily. Every single day, the sun rises and the sun sets, the tides come up, the temperature fluctuates, so we can measure daily changes that occur on very short time scales. Daily, what else we got? Medium, annual or longer. Forest fires burn every 150 years to 200 years. Volcanoes can have volcanic eruptions. Mount Kilauea erupts some years, not other years. So forcing events happening in shorter time periods, and then long time scales, like the movement of biogeochemical cycles. Let's take carbon, for example. A volcano erupts and ejects carbon dioxide to the atmosphere. Stays in the atmosphere as a greenhouse gas and then is absorbed into the ocean. In the ocean, it goes through the carbonate buffering system, and that carbon is uptaken by marine phytoplankton used to create their tests or their microscopic shells that then deposits at the bottom of the ocean, lithifies into rock, which then, over geologic time, travels across Earth's surface, subducts, partially melts, and erupts in a volcano again. This is the carbon cycle, and this takes millions and millions, tens of millions to hundreds of millions of years. Tectonic plates. J. Tuzo Wilson developed a model for supercontinent development, where all of Earth's continents come together to form a supercontinent, and then they break apart. This is on very long timescales. So what is the time scale? Is it daily? Is it years or hundreds of years? Is it millions to tens of millions of years? Now, there's always anomalies, departures from normal behavior. A forcing event creates a feedback in response. Tipping points can be reached, which upset the natural balance and create a new equilibrium. Anomalies occur through time, and it's important to have the background normal and understand what is happening in relation to a standard or a set of averages. Again, we come back to climate anomalies because it's such a big issue. All roads lead to climate change, it feels like at this point. But hey, if we have such a pressing, critical issue, why not use our understanding to help solve this climate crisis that is upon us? Quick review. We're measuring Earth systems through time and space. Through space, we can look at it affecting the entire planet, affecting regions independently, or smaller local differences. Time, is it happening on a daily? Like we can go measure the tides. For annual, years, hundreds of years even, or long, millions to tens of millions, even billions of years. So how do we measure these things? Well, we can actually put instruments. It's a measuring instrument. I'm just going to label it measure. And create ground-based measurement. These are highly accurate, providing detailed records that can give us information on shorter time scales and help us to understand variability across space when you compare different instruments together. Less accurate, but more comprehensive, is to use remote sensing. Satellites in the sky collect a ton of data for what's happening on the Earth. And using these remote sensing techniques. They're very expensive, difficult to develop and maintain, but give us a wide range or great coverage of the Earth. And NASA has been doing a few things. They have the Earth Observing System, so a whole series. If you're only like, oh yeah, that's a good idea, let's put some satellites up there and measure. So the NASA Earth Observing System, EOS, has a bunch of different satellites collecting a ton of data, and we can go on the NASA website and look at this data. It's all open source. Nearly all of it is free and public. So if you're wondering about anything, sea surface temperatures, ocean salinity, global climate average temperature variability, it's all on here. Let's check it out. And then space weather. So these are all measured, able to be measured on Earth. How about space? Which, if you remember from Earth as a system, the exosphere. So not only do we want to know what's happening on Earth, we also want to know what's going on in space, including impacts to Earth's magnetic field, cosmic radiation from the sun and the Milky Way. We're very interested in asteroids right now. Not only are we going to be impacted by an asteroid, but what kind of organic molecules can we find on asteroids? And then geomagnetic storm potentials, because wind and flares from the sun have the ability to strip and impact Earth in negative ways. So monitoring the exosphere, measuring what's happening out in space, is also critical for understanding what's happening on Earth. Okay, so the Earth is a system made of subsystems, interrelated parts working to form a whole. These parts interact through forcings and feedbacks. Matter and energy is stored in sinks, and when critical points are reached, we call them tipping points. In order to understand this, it's important to measure what is happening, the variability of these subsystems. And we measure this variability through time, local, annual, millions of years, longer, large timescales, and through space, the Earth as a whole, global, regional, and local, so that we can gain an understanding, a holistic understanding of how our Earth works and how and what we can predict to happen to our Earth in the future. Thank you so much, and I'll see you again.